In the video dedicated to the study of sinusoidal functions, we obtained the following representation of waves that present variations in space and time, in which the angular frequency omega is the product of 2 pi times the frequency, and the wave number k is the quotient of 2 pi by the wavelength lambda. We will then apply this result to describe the movement of air particles in response to a flat impeller vibrating with a sinusoidal displacement to produce a pure tone. In this figure, we have idealized the situation by considering that we have an array of uniformly spaced particles. This will allow to better visualize the dynamics of the displacement of these particles and the resulting sound wave propagation. Here is the result. It is observed that the impeller gives the particles a longitudinal sinusoidal motion around their initial position. The average distance of each particle to the impeller is maintained, but its motion gives rise to a distribution in which zones with high particle concentration and zones with low particle concentration alternate, and the consequent increase and decrease of pressure with respect to atmospheric pressure. This distribution propagates in the air away from the impeller with a speed of about 340 meters per second. In this animation, we have used green to represent the waveform of the displacement of the particles with respect to their rest position, and blue to represent the waveform of the pressure variation. Notice that the second one is 90 degrees behind the first one. This delay is logical, since the increase in pressure is a consequence of the displacement of the particles. In the figure, it is possible to identify zones of positive displacement of the particles in the direction of propagation and of negative displacement in the opposite direction of propagation. It is also possible to identify zones of pressure higher than atmospheric pressure, compression, and zones of pressure lower than atmospheric pressure, rarefaction. You will have noticed that at the beginning of the animation there is a flicker, which we will explain next. To give an opportunity to observe the beginning of sound propagation, we will proceed to a slower animation of the initial cycles of the impeller motion. Note that upon impact of the impeller with the first column of particles, the particles move and impact the particles in the second column, which in turn move and impact the particles in the third column, and so on. All this in a very short time. Thank you for watching this video. We hope you found this look at the phenomenon of sound production and propagation interesting.